Hello and welcome to this section of the Circuit Analysis Tutor where we are continuing to deal with mesh currents and solving mesh current problems that have dependent sources. So here we have on the board a more complicated problem where we actually have not one but two dependent sources, and not only that, one of these sources is a dependent current source and one of them is a dependent voltage source. So notice what we have here is we have a constant current source of 19 amps here. We have a 240 volt source oriented kind of backwards where the positive side's down. We have the resistors and then we have these dependent sources. So the value of this current, for instance, is 2 times whatever the value of this current happens to be through the 5 ohm resistor. And the value of this voltage source is going to end up being 4 times the value of I sub 4, which is running through this source over on the end. So this problem is interesting for a couple of reasons. One, it's because it's got not one but two sources, dependent sources. And number two, it's interesting because there are different types of dependent current sources. One is a dependent voltage source, one's a dependent current source. But as we've said more than once up to now, just start tackling your problems in the same way. If you don't know how to do it, if it looks more complicated, just roll up your sleeves and go back to what you know. Everything I'm teaching you is fundamental skills. So just go back to your fundamental skills and see where it takes you. And if you have to make little detours along the way, then great, but don't throw your hands up. So here we have 1, 2, 3, 4 meshes. So one more mesh than we're typically used to dealing with. So let's go in and label them. This one we're going to call I sub A. This one up here, we'll call it I sub B. This one down here, we're going to call it I sub C, and this one over here we'll call I sub D. And what we're trying to actually calculate in the circuit, we want to find the values of all of these currents that we have labeled. Notice that we have this guy, I1, I2, I3, I4, I5. Some of these currents are actually used in the dependent sources to get their values. But what we're trying to find is calculate these currents, right? 1, 2, 3, 4, and 5. And also, when you are asked to calculate the value of some current that's labeled in your drawing, then you need to calculate the value of that current from that point of view, from the point of view of that current. So in other words, this is I sub 1, it's going down. So I need to calculate it as if it were going down. If it happens to turn out to be a negative value, then it just means that it's negative, opposite the direction that was actually drawn here. But that's nothing wrong with that. It just means we're assuming it's going down. If we get a positive value for I1, then that's the actual direction I1 is going. If we end up calculating a negative value for I1, it just means that the actual current here is going up, opposite to what we have actually labeled. So we're calculating these values based on their point of view. So let's go ahead and work on I sub A. Right? So let's look at mesh A. So we're going to sum around through the source here and then through the 40 ohm resistor, just like we've been typically doing. But we run into a roadblock right away because this is a current source. We do not know the value of the voltage, so we can't sum it up. But then we realize, look, this is a current source on the outside boundary of a mesh. So I sub A, which is circulating here, is going in the same direction as this 19 amp source. So I sub A is actually equal to 19 amps. So literally, you can write down for your first mesh current equation, I sub A is equal to 19. It's a fact. It's given to you in your drawing. It would be the equivalent of basically drawing all of your mesh currents and then the problem just telling you I sub A is 19. Well, that's kind of a lame way to do a problem. So you set it up this way, and so the student needs to realize that this is a mesh here, this is a mesh current, this is a current on the outside boundary, so IA must be 19 amps. It is a mesh current equation. It's just trivial because it gives you the value of IA already. So immediately we know this problem is going to be a little bit easier to solve than we initially thought because one of our 4 meshes is basically solved to begin with. So let's go and work with mesh B, like this. All right, mesh B is up here. Now let's go ahead and start here and let's work our way around like this. So what we're doing is we're going from negative to positive this direction. So we're going to treat that as negative, and the value of this voltage is 4 times I4. So negative 4 times I4 is the voltage rise, really. So we stick a negative there across this guy. Then we get down to the 10 ohm source. And when we get to the 10 ohm source, we assume the current's going this way as we walk around, which means it's got to be IB minus ID to give us the current going in that direction. If the current really is going this way, then we're going to have a voltage drop plus to minus. So we're going to treat it as a positive, and it'll be IB minus ID times 10. IB minus ID times 10. Now also, as you're doing your mesh currents, I've told you this many times, I want you to ignore these labels here. These I1, 2, 3, 4, and 5, that's at the end game of the problem. Once we get our mesh currents, then we go back and figure out how it lines up with these other labels that were given in the problem statement, okay? You don't get yourself confused coming through here and saying, well, I3 is going this way and I4 is going this way, so how does that? No, you leave all of those for the end. Right now, we're only dealing with IA, B, C, and D. The only reason we have an I4 here is because this is the actual voltage across the sources in terms of it, so there's no way to get around having that in this equation. So we have the voltage drop across here. Now let's move over here. Voltage drop across here. If the current's going this way, it's going to be a positive voltage drop. Then it would be IB minus IC, which is fighting it. So it's IB minus IC times 5. Right? And so we've completed everything. We just set it equal to 0. So let's go and simplify this. We have negative 4 times I sub 4 plus, distribute this in, we'll have 10 times IB minus 10 times ID. Over here, we'll have 5 times IB minus 5 times IC, and this is all equal to 0. So let's simplify this, collect terms, negative 4 times I4 plus, here, let's see, do we have any IAs? Nope. Do we have any IBs? We have 10 plus 5. It's going to give us 15 I sub B. Do we have any ICs? There we do. Negative 5 IC. Do we have any IDs? 10 ID. And we set it equal to 0. So we have this guy there, but there's something nagging me about having an I4 in here. I mean, ultimately, we know we want to solve the mesh currents for IA, IB, IC, and ID. Those are the meshes. IA is already solved for, so really we really only need IB, IC, and ID. We know that this I sub 4, in terms of solving our mesh current system, is totally extraneous. So let's go and look for some sort of constraint equation to help us get rid of it. Where is I4 at? I4 is down here in the circuit, right? How can we relate I4 to any other variable in the problem? Well, notice that it's part of mesh that includes I sub D. Notice that it's on an outside leg, so ID, which is this mesh current, is actually equal to I4. So what we know from looking at the drawing is I sub D is equal to I sub 4. So we can actually take that and stick it right in there and eliminate I4 from this guy altogether. And that's the simplest constraint we can really do. So let's put it in here. So negative 4, I sub 4 is basically ID. Like this, plus 15 IB, the rest of it's just copying, 5 IC minus 10 ID is equal to 0. And now we simplify again. So we have IB and IC, 15 IB minus 5 IC, and now we simplify this guy, negative 14 ID equals 0. So we have 15 IB minus 5 IC minus 14 ID is equal to 0. And this is an asterisk here because this is the mesh, basically this is the mesh equation, the simplified form of it for mesh B up at the top. And all we did was walk around doing everything there, but we noticed that this guy, this I sub 4, is not going to really in the end be what we're solving for our mesh currents. The end game of the problem, yes, we'll calculate it, but for the mesh currents, all we care about is IA, IB, IC, and ID. So we know we need to get rid of that I sub 4 in this equation. So we go down here and we realize, oh, well, that's just equal to ID, and we get rid of it. All right, so then we're ready to rock and roll and continue on. So we have mesh for A, we have a mesh for B, and now we have a mesh for C and D. So let's look at C and see what we have. We could walk around these guys here, and then when we get to this current source, we're going to be stuck again because we do not know the voltage across this current source. And if you think about it, if you go through ID and do the same thing here, once you get to ID, you're going to get stuck here doing exactly the same thing because you don't know the voltage across that current source. So if you remember back a few sections ago, we did another problem like that where we had a current source straddling two meshes right on the boundary. And I showed you that if you don't know the value of the voltage drop across that source, then you can just make it up, because you know there has to be some voltage across it. Just label it, and then what you could do if you wanted was label this as a voltage, and then you would just put it in a mesh equation for I sub C, and then you would put it in another mesh equation for I sub D. Both of these mesh equations would have the voltage V that you made up in there, and you could then add those equations together to eliminate V. We did that for the node voltage method, something similar. We've done it for the mesh current method. That works fine. You could literally do that for this problem. It doesn't matter that it's dependent source. It's going to work just fine. No problem. But it's a good opportunity to show how a super mesh would come in handy, because we also said that when you're confronted with something like this, you can introduce a super mesh. Basically what you're going to do, instead of doing a loop around C and a loop around D, you're going to basically do a loop around the whole problem area. In other words, you're going to do a loop all the way around this super mesh here, kind of ignoring what you have in the middle. And you might say, well, how can you do that? Well, there's two reasons that I can give you to do this, and you should be able to come up with them on your own based on what we've learned so far. The first one is, mesh current method is really just Kirchhoff's voltage law. You're summing up the voltage drops around these little meshes that we have, and you're setting them equal to 0. That's all you're doing. And I already told you that, yeah, it works for this mesh and this mesh and this mesh, but Kirchhoff's voltage law works for any closed loop path in a circuit. This is just a larger mesh than the ones that we typically deal with. But the sum of the voltage drops around that mesh should always be 0. It's a fundamental law of physics. That's what Kirchhoff's voltage law is, right? So that's one reason why you can say it works. The other reason is, you might say, well, how can you just avoid this whole component here and not even deal with it? Well, it's because of what I told you before. If you do individual mesh equations labeling a voltage there and you add them together algebraically, you can get rid of that variable. You can eliminate it, because don't forget, even though mesh current method is summing up these voltage drops, all we really care about in the end is finding IA, B, C, and D. And this value of this current, yes, it's important in the circuit as far as the function, but you can eliminate it from the equations and still get what you want as an answer. So much like in physics, way back in physics 1, when you had to introduce, the velocity of something, to calculate something. And then in the end you figure out, well, velocity wasn't that important. Or a better example would be the mass of something. Maybe you think you need to introduce the mass of the object to calculate the answer, but then you realize, well, you don't really need to know the mass. The mass cancels. The mass isn't even important in the problem. So this, yes, it's important for the function of the circuit, but in the context of writing your mesh current equations, you can write a super mesh and kind of avoid it, because algebraically you can get rid of it anyway if you write these smaller meshes. So that's the theoretical version. The practical version is, we know this is going to be a problem area, we know it's a current source, we know it's a boundary of two meshes, so we know we can avoid it. That's sort of the take-home thing. So let's go over here and write that super mesh equation. So I'm going to write down, just to let you know what we're doing, super mesh. All right, and we're going to start at the 40 ohm resistor here. Now notice, we've already labeled I sub C, we've already labeled I sub D. When you write your super mesh equations, you still honor I sub C and I sub D as you have drawn them. It's just the path you take is larger. So when we go through the 40 ohm resistor, we're going to assume the current's going up, so it's going to be IC minus IA. So what we're going to do is IC minus IA, that's the current, times R is going to give me that voltage drop. All right, and then we get to the 5 ohm resistor. We're going to assume the current's going this way, so it's going to be IC minus IB, that's fighting it. So it's going to be IC minus IB, that's fighting it, times the 5 ohms. Then when we walk our way around to the 10 ohm resistor, it's the same thing. We're assuming there's a voltage drop here, so we assume the current's going this way. So it's going to be ID. Notice there's an ID here that's governed here. ID minus IB, that's fighting it. So what you're going to get is ID minus IB, that's fighting it, times 10. And then finally you're going to walk through this guy. You're going to go from negative to positive. Anytime you go from negative to positive, a voltage rise, you treat it as negative in your Kirchhoff voltage law. So it's negative 240 equals 0. Make sure you understand the super mesh. Basically, as I said, you honor IC and ID. So when you get to the 40 ohm resistor, it's IC minus IA. When you get up here, it's IC minus IB. When you get over here, you've totally skipped this. When you get over here, you're not dealing with IC anymore. I sub D is the mesh current subtraction that you do here, because that's what's governing this 10 ohm resistor. So let's go ahead and simplify here. So we're going to have 40 I sub C minus 40 I sub A. Over here, we're going to have 5 I sub C minus 5 I sub B. Over here, we're going to have 10 I sub D minus 10 I sub B. And over here, we'll just have the negative 240 right there. Okay, so let's go ahead and simplify. So we have an IA over here, negative 40 IA. Okay, and now we look for any IBs. So we have one here and we have one here that's negative 15 I sub B. Now we look for any ICs. We have a 40 plus another 5 is 45. I think that's all we have. So we have a 45 I sub C. And then we look for any IDs. We have one here, 10 ID, like this. And then the negative 240, we just move to the other side, like that. So there we go. So that's our next mesh equation. So the first mesh equation we had involved B, C, and D. This one involves A, B, C, and D. So we're saying, well, we're probably on the right track, but then you realize I sub A is already known. We already know that I sub A is a number. In fact, we could have just put 19 in along the whole way. I just like to do it in terms of variables. So we can actually eliminate I sub A immediately by remembering that I sub A is 19. So when we put this in here, we're going to have negative 40 times 19, right? Minus 15 I sub B plus 45 I sub C plus 10 I sub D is equal to 240. And then when we multiply the 40 times the 19, and then we get that number, and then we move it over to the other side, what we're going to have on the left-hand side is negative 15 I sub B plus 45 I sub C plus 10 I sub D. When we get this number as a negative, we add it to the other side. On the right-hand side, we're just going to get a nice even 1,000 on the right-hand side. Okay, so this actually is a very important mesh equation. So this is the super mesh equation, and notice what variables it has. It's got an IB, C, and D. This equation's got an IB, C, and D. So we still, even though we've made great progress, we still don't have enough to actually solve this because we have 2 equations and 3 unknowns. And we really have no idea what B, C, and D are. So we can't do any tricks. It's not given to us in the drawing. But what you need to kind of get in the habit of is anytime you have a super mesh, and we did this once before, anytime you have a super mesh, you're going to have a constraint equation, another one pop out that's going to directly relate to your super mesh. In this case, we skipped over this current source here. And earlier we were talking about, well, how can you just skip over that? You didn't even take it into account. Well, this is where you take it into account. Once you get to this point, you realize you can't solve the circuit, so you go back and you say, well, I need another constraint. And you look at what you have and you realize that this current source straddles 2 meshes. It straddles the C mesh and the D mesh. So what you can say is this value of this current is equal to ID, which is going in the same direction, minus IC, which is fighting it. So for the constraint, change colors. What you're saying is the value of this current, which is 2 times I2, is equal to ID in the same direction minus IC. ID minus IC. Right? So ID minus IC. And then you look at this and you're like, well, this is a great constraint, but it doesn't totally help me because now I have an I2 involved, right? How do I get rid of that? Because ultimately, I want to solve these mesh equations in terms of A, B, C, and D. Of course, I know what A is already. It's a given already. We've already solved it. So I look and I try to figure out how can I get rid of I2? So I go and I look around. Where's I2? I2 is right here. I2 is defined to be traveling on the boundary between mesh C and mesh B. And it's going in this direction, which means I2 has got to be IB minus IC, which is fighting it. So we also know that I sub 2 is equal to IB minus IC. And that's just given from the drawing. So what we do then is we plug it in here. So let's do that. So we have 2 times I2, which is IB minus IC, equals ID minus IC. So we multiply through 2IB minus 2IC is equal to ID minus IC. All right, and let's just move both of these over to the other side of the equal sign. So the 2IB will stay the same. The IC, I have a -2 here. When I add it, I'm going to be adding a positive number, so I'm going to have -1 IC on the left-hand side. ID is going to become negative, and this should be the constraint. 2IB minus IC minus ID is equal to 0. This is the third equation. Notice that now I have an equation in terms of B, C, and D. This equation is in terms of B, C, and D. This equation is in terms of B, C, and D. And those are 3 equations and 3 unknowns. 2 of the equations came from mesh current equations we're traveling around. The third one came from a constraint on what we skipped in the super mesh. This is the same pattern as always. In the node voltage method, it was the same thing. If you do a super node, then you're going to end up having to write a constraint that's going to deal with something that you skipped over in the super node. Same thing with the super mesh. You skip over something, great. Then you're going to write a constraint based on usually on something that you skipped in the super mesh. And that leads to a third independent equation. Okay? So now we need to solve these for B, C, and D. IB, IC, and ID. So we solve it with matrix methods. It's my favorite thing in the world. And so matrix A, okay, the first equation is this one, 15, -5, -14. 15, -5, -14. Okay, the second equation is this one, -15, 45, 10, -15, 45, 10. The third equation is this one, 2, -1, -1. 2, -1, -1. And don't forget that we are solving for IA, IB, IC. And the B matrix is what's on the other side. For our first equation, it was just 0. And then after that, it's 1,000 and then 0. So it's 0, 1,000, and then 0. Okay? So we multiply both sides by the inverse of matrix A, which is going to lead to the answer IA, IB, IC is equal to the inverse of matrix A times the column vector B. When you put this in a calculator and calculate its inverse, you're going to get something that looks like -0.070, 0.010, -0.150, 0.018, 0.026, 0.010, 1.160, 0.120, and 1.200. This is the inverse, and then we're still multiplying it by this guy, 0, 1,000, and 0, like that. All right, so at the end of the day, when you do this matrix multiplication, IA, IB, IC, and you'll have to excuse me from force of habit. You know, I said A, B, and C because all of our equations so far have been like that. This is B, C, and D. And so this is going to be B, C, and D either. Just goes to show you everybody makes mistakes. So B, C, and D. And so ultimately what we have solved for is not A, B, and C. It's B, C, and D. So what we've now found is that IB is equal to 18 amps. IC is 26 amps. ID is 10 amps. Now we have one more current. IA, where's IA? We found that way in the beginning. It's 19 amps. Okay, these are the answers. So IA is 19 amps, IB is 18 amps, IC is 26 amps, ID is 10 amps. Notice that all of these mesh currents are positive, so that means the directions of these guys are more or less in the directions that we've drawn them for IA, B, C, and D. Now the challenge is, how do we find and convert these mesh currents that we've calculated to these labeled currents? See, I can label a current anything on there, like, hey, what's the current this direction? Well, then you have to look at the point of view of that current and see, okay, is it really going that way, or is it going opposite, in which case it would be negative. So we're going to go through I1, 2, 3, 4, and 5 and figure out what's going on here. So let's remind ourselves what the mesh currents are that we've calculated, just so we have a reference here. So we have IA is 19, IB is 18, IC is 26, and ID is 10. So these are the mesh currents. Now let's go and figure out I sub 1. I sub 1, where is it? It's over here. And it's going down. That means that in terms of my mesh current, it's got to be IA minus IC. That's the only definition that makes sense because IA is defined to be going down, so it's going to be IA minus IC. So we say IA minus IC. Here we have IA is 19 minus 26, IA minus IC. And look what you're going to get is negative 7. So I sub 1 is actually a negative number, negative 7 amps. What does it mean? It means that even though the problem gave you a current labeled down, it really means the current's not going down. The current's actually going up. And you define this in terms of your drawn mesh currents and let the math take care of what direction it's really going. I sub 2, let me switch colors to make it a little bit easier to read. I sub 2, where's that guy at the drawing? I sub 2 is here. It's going this way. That means it has to be IB minus IC, which is fight again. So it'll be IB minus IC. IB is given as 18 minus 26. Look, we have another negative number here, negative 8 amps. So that means, again, I2 is not really going this direction. It's really going that direction, 8 amps. All right, now let's go back I3. Where's I3 at? I3 is here. It's going this way. That means it has to be IB minus ID. IB minus ID. IB is given by 18 minus ID is 10. So that's a positive 8 amps. So that one means that I sub 3 is actually going this direction, the direction that we've drawn it. And then we'll round out things with the easier ones, I sub 4. I sub 4 is defined to be going down this direction, which is the same direction as my mesh current ID. ID we've calculated to be 10 amps. So it's positive 10 amps going that way. And then finally, I sub 5. I sub 5 is going this way, that way, which is the same direction as I sub B, so it's equal to I sub B. I sub B is equal to 18 amps. So it's positive 18 amps. So we have negative 7, negative 7, negative 7, negative 8, positive 8, 10, and 18. Some of them are negative. That just means that it's actually traveling opposite the direction that it's labeled in the drawing. Some of them are going positive. But notice that we ignored I1, 2, 3, and 4 and so on the directions and all that until we were done calculating our mesh currents. It's very important for you to remember because a lot of students get wrapped up in what's labeled on the drawing. Half the time we give you a label on a drawing and a problem, it's backwards on purpose. I want to see if you get me the negative number. I want to see if you know enough to tell me that it's negative and that means it's going opposite, right? That's very important into understanding for you. So this was, a little bit challenging, but not too bad. So we define our 4 meshes. Immediately we find out that one of our meshes is trivial. We have the answer. The top mesh is pretty easy, but then we realize this voltage source is in terms of I4. So once we get it all simplified, we realize I4 is equal to ID. We plug it in there, and we get a simplified equation for mesh B. Then we get over here, and we realize if we do a mesh here or a mesh here, we don't know the voltage. We could introduce the voltage and then add those equations to cancel. If we did that, we would end up getting this equation, which is what we want to end up with anyway. But if you don't want to do that, you can just draw a super mesh going all the way around it, and we literally walk around this boundary doing the same thing that we always do. We just skip over the problem area. And we end up with something like this. Then we realize we have an IA as part of our equation. We know IA is a number, so we just use that fact, and so we get an equation in IB, IC, and ID. So now we have 2 equations with 3 unknowns. The 3 unknowns are B, C, and D. We know we need to go ahead and find another equation, so we go back to our super mesh and see what we skipped over. This current its value is 2 times I2, and it's equal to ID minus IC. So we use this fact here. Once we know that we do this, we go and see what can we learn about I2. I2 is way over here. It's the difference of these two currents, B and C. So we plug this in, do the simplification, and we end up with a third independent equation with B, C, and D as the variables. We stick those guys in a matrix, and we get the values of B, C, and D, which we write down, and then we also know what the value of I sub A is equal to. All right? And then once we do that, we have all of the mesh currents. They're all positive, so they're all basically the same in that way that we've drawn them. And then we look at our drawing arrows and we figure out, okay, which way do I have to subtract to get the current to go that direction? Do the subtractions, get all of the currents. And that, my friends, is how you do mesh currents in circuit analysis. It is involved, but only because there's sign conventions and because there's super meshes and constraint equations and things like that. But I hope you can see past that and realize that mathematically it's not that hard. It's just a matter of you taking your time, not making silly sign errors, and understanding, and I think using the matrix methods that I've been teaching you are going to really help you out as well. And I think we've done enough of those where you can see that, you know, it's not that many steps to write a matrix down and then take the inverse and solve it super fast. You can do it on a test, and I think it's better than sticking these equations into an equation solver most of the time anyway. If you have a current source that's boundary between two meshes, then use a super mesh and then go back and write a constraint equation on it, much like we've done today. I feel confident that you have the tools after watching this video series in node voltage and mesh current methods for some of the core fundamental techniques of circuit theory, right? Node voltage and mesh current, I'm not going to say one's better than the other. They're just different tools. Sometimes it might be easier and lead to fewer equations to use node voltage method. Sometimes it might be easier and lead to fewer equations using mesh current method. It just depends on the problem. And you can use both methods for pretty much all problems anyway. So expect on your test and on your homework to be asked, use a node voltage for this, use the mesh current for this, and you have to do it that way. So just make sure you've mastered both techniques. Definitely make sure you can solve this problem, and make sure you can solve all of these problems that we've done in all of the sequence with mesh current and node voltage. And I'd like to close by saying that there's a journey ahead of you. We still haven't even talked about capacitors and inductors. We're going to do that very soon. And once we get into that and start talking about sinusoidal, sources, you'll find that these mesh currents and node voltage techniques are all going to be applicable when we start talking about sinusoidal steady-state analysis with even more complicated circuits with capacitors and things like that. So everything you're learning here, the super meshes, the super nodes, the sign conventions, everything is completely applicable. So please make sure you understand it before you go on. And in the next batch of lessons that we do in the future, we're going to talk about Thevenin equivalent circuits, Norton equivalent circuits, which are ways to simplify circuits beyond what you already know. And then we'll start talking about capacitors and inductors and learning about how they work and how they fit into the grand scheme of using them into circuits. I'm Jason with MathTutorDVD.com. I hope you've enjoyed this set of videos. Please make sure you understand how to do everything, and then roll up your sleeves and work those extra problems yourself to get your own confidence up with node voltage method and mesh current method in circuit analysis.